Okay, so question 8 is saying a small boy of mass m revolves in a horizontal circle at a constant speed at the end of a rope of length 1.2 meters. As the body revolves, the rope describes the surface of right circular cone as shown below. If the semicircle is at 30 degrees, calculate the speed of the mass m in meters per second to the speed of the mass m in a rad per second and the time it takes to complete the revolution. To complete a revolution, complete one revolution. I don't know what they wrote here, but they meant to complete one revolution, I guess. Okay, so what are you going to do here? If it was you only, what were you going to do here?
In complete honesty, I kind of had issues answering this question when we were writing the finals, so I didn't finish this part.
You didn't finish again.
No.
Okay, so first, this is circular motion or rotational motion. So what are we supposed to do first? Let's bring out a free body diagram. So from there, they've told us to say uh, it's like that. Even here is like that. Then it is forming that down there. Then on the middle here, we have 30 degrees here. I guess this is what they've wrote. The length of the rope is 1.2 meters. And what else? Uh, we've been also given the mass, I guess. They haven't given us the mass of the ball, right? No, no, they've just given us the length. Okay, so that is all that we have. So imagine if my ball is here, as they have given it, the ball is there. And this is the rope, which is 1.2 meters long. What kind of forces are we going to put on this diagram? What kind of forces?
I think we're going to put centripetal force.
Okay, so there's centripetal force, yes, but where is the centripetal force going to point? The direction is very important, eh?
I think it's going to be moving to the right.
To the right, the centripetal force. Okay, so there's length here of 1.2. We'll say that. Then there's tension in this rope, but we're going to have to resolve this tension. So we have tension in the y-axis here, like that, going up. So since this is forming Z angles with this, that means even this one is 30 degrees, right? Then the other
Yes.
tension is pointing in this direction, like this. So this one, which is adjacent to the 30 degrees, is going to be carrying a cos. So we'll have T cos 30 here. It is adjacent to this angle 30, and this one, which is our, is going to be T sine 30 degrees, like that. Okay, so what else do we have? We have mass of the bulb. We have mg acting in that direction. Then to balance up everything, what else do we have? We have the centripetal force, of which where is the centripetal force pointing? Just give it a try to balance up everything. Where is the centripetal force pointing?
Um, I think I'm going to say left this time.
Okay, so here we have the centripetal force. What is the formula for centripetal force? So I'm going to draw this diagram here again to simplify everything. So I have t cos 30 there, and I have this here. I have t sine 30 here, tan 30 degrees, and I have mg here. I have the centripetal force there. The formula for centripetal force?
Uh, the formula for centripetal force is Fc equals mv squared over r.
Okay, so I'm just going to plug mv squared over r here. Okay, and from here, we can say for our forces in the y-axis, we're going to say t cos 30 is equal to mg. Since these guys are at equilibrium, the mg is going to be negative, and it's going to equate to 0. But if I write it like this, I've just written it directly because it is simple to deduce like that. Okay, so tension is going to be equal to mass times gravity divided by cos 30, like that. Am I correct? Then in the y-axis, I mean in the x-axis, we have uh, t sine 30 being equal to mv squared over r, like that. That means we have v for the velocity, we have m for the mass of this guy that we're talking about, and then we have r. R is the radius of the circle. So where are we going to get the radius of the circle? Okay, this circle which is here. Where are we going to get the radius? So here I can say it's much easier to get the radius. Why? It's because they've already given us the length of the string there. So if I take this as a right-angled triangle, I'm going to remain with this, something like this. And then they've given me to say this is 1.2. I'm looking for this as my R, and then I have my angle there as 30 degrees. What am I going to, or which formula, or which rule am I going to use in order for me to get the R? I can simply use the sine rule, right? Because you know, to say sine theta is equal to opposite, of which this is the opposite, the R, over hypotenuse, of which the hypotenuse here is the 1.2 there. So I'll say my R is equal to 1.2, like that, sine 30 degrees. And this is going to give me how much? What will be the answer?
0.6.
0.6. Okay. So uh if you look at these equations now that we have here, where is it? Okay, we have this equation here. We also have this equation here in the x-axis. We know to say tension is equal to this. So we can get this tension that we've calculated here and plug it into this equation. And what are we going to get? We're going to get, let me put it here. Tension is mg over cos theta multiplied by, what are we multiplying with? We're multiplying with this sine theta, which is here. So multiplied by a sine 30 degrees. And this is going to be equal to what? It is going to be equal to mv squared over the value of our r is 1.2 sine 30 degrees. Okay, like this. Like this, we are trying to find velocity. Our goal is to find the initial velocity. So what are we going to remain with? If we do so, if there's such English, what are we going to remain with? Because this is the same, our right-hand side of the equation, this one, is the same as we have, since we want to make V for the subject of the formula, I'll say this is equal to M over 1.2 sine 30 degrees, and this is multiplying what? V squared. So if I want to remove M over 1.2 sine 30, I'll multiply by the reciprocal of that. So it should be 1.2 sine 30 degrees over M, like that. So the M and the M cancels out here, and this and that cancels out. So I remain with V squared is equal to mg over cos 30 degrees multiplied by sine theta, which is sine 30 degrees, and this multiplying with 1.2 sine 30 over m, like this. So from here, what can we see? We can see to say that this m and that m is also getting eliminated from our equation. Then what else do we have? We have sine and, okay, so the sine is a numerator, or like that. Okay, so we're going to have v squared being equal to, if you want, you can write the whole thing, but I've already reduced, so I'm going to remain with g sine squared theta g sine squared theta, which is theta is 30 degrees, multiplied by 1.2, like that, over cos 30 degrees. Cos 30 degrees, like that. Okay, from here, where else can we go? We know to say gravity is 9.81, so G is equal to 9.81, like that. So are you able to find the V from this part or from here? Can you find the V?
Uh, let me try. Let me try to find it.
Okay, fast. Which means that is going to be V squared is equal to 1.2 multiplied by 9.8 sine squared 30 degrees over cos 30. Okay, cos 30 degrees, like that. Okay, so let me also be punching it here. Okay, so 1.2. Let me start with sine squared 30. Sine squared sine squared 30. What have you found there? So the numerator is equal to um, 2.94, and this divided by cos 30 degrees, and this should give you 3.39 like that. So we're going to say our v squared is equal to 3.39. Well, this is our v squared. And what are we going to do to that? We're going to introduce our square root on both sides of the equation. So I'm going to have this like that even here. So I'll get my v is equal to 1.84 meters per second like that. Okay, so this was a very, very long process. So v, which is the final velocity, I mean, not the final velocity, but the velocity of the mass that we've been given was v is equal to 1.8 meters per second. What else have we been asked to calculate? Been asked to find the speed of the mass in rads per second. Okay, so this one is pretty directly. In rads per second, if you want to convert this velocity into rad per second, what are you going to say? Or which formula do we use? Converting rad per second into, I mean, converting meters per second to rad per second. What is the relationship between angular velocity and linear velocity? I talked about it last time, and I don't know how you just forget like this. So I said V is equal to what? It's equal to R multiplied by W, of which W is the angular velocity that we are looking for. So V, we found to say it's 1.84. So we're going to say W is equal to V over R. Is it true? Yes, it should be like that. So found our R to be 1.2 sine 30. So W is going to be equal to 1.84 divided by 1.2 sine 30 degrees. And this is going to give us what, or what will be the value of that? Hello, you've gone quiet.
Sorry. I'm punching it now. So that's 1.89 divided by 1.2 sine theta, correct?
Yes.
Okay. I found 0.7. 875. So if you round it out, it's 0.79 rads per
Yeah.
second.
So this will be equal to 0.79 rads per second, like this.
Yes.
Okay, the next one is saying calculate the time it takes to complete a revolution. Time for one complete revolution. So, which formula can we use in order for us to find the time for one complete revolution?
Mm,
Velocity is equal to distance over time.
okay.
Which distance are we going to use? It's the circumference of the circle that is being formed here. Where is it? Okay, the circumference of this circle is the distance that we are looking for. And the formula for circumference of a circle?
2 pi r squared.
Okay, circumference of a circle will be equal to, okay, you said it is equal to what?
2 pi r squared.
2 pi r squared or just 2 pi r?
I think it's 2 pi r squared. I'm convinced it's 2 pi r squared.
Hmm. Because we can use two formulas. It says I use 2 pi d. Oh yeah, 2 pi d or 2 pi r squared, right?
Yes.
I think so. Kindly check for me. 2 pi r squared.
Okay. Uh, so I'm looking for the formula for circumference of a circle, correct?
Yes.
Okay. 1 second. Formula for the circumference of a
Okay,
circle.
so it's 2 pi r.
That's 2 pi r.
2 pi r squared is for area.
Ah, okay.
Okay, so circumference is equal to 2 pi r. So let's calculate. Circumference is 2 multiplied by pi multiplied by r, of which r is equal to 1.2 sine 30. 1.2 sine 30 degrees, which is 0.6. So 2 pi 0.6. So I'm multiplying these guys here like that. This is going to give us a circumference of how much? Okay, so I'm getting circumference which is equal to 3.77 meters. 3.77 meters. I don't know if you found the same thing. So, since we've already gotten the velocity, we're going to say velocity is equal to distance over time, of which we're looking for time in this case. So, we're going to say this is equal to Vt being equal to distance. We've calculated distance, so over V over V. So, which means our time is equal to distance over velocity. Okay, so our time is equal to the distance is 3.77 over velocity, which is 1.84 meters per second. This is meters. The meter and the meter goes away. Our time will be equal to, what will be the time?
I found 2 seconds when I rounded off.
Okay, so two. There's no point something.
It was 1.99 when I punched it in, so I found 2 seconds.
Okay, so 1.99 or 2 seconds. Okay, let's just put 2 seconds. It's okay. Okay, like this. Any question?
No. I wanted to clarify something on questions where, like, let's say, okay, how do I put it? On questions where, let's say, as you've been saying, there are certain forces that are in equilibrium. Which topic exactly should we focus on if we're a bit confused on forces that are in equilibrium?
There is a topic, equilibrium forces, under vectors, I guess.
Okay.
Yes, but in case of your physics, is that physics 1010 or physics 1015? There's a topic just after, I think, work, energy, and power at the end of the semester. That's where they teach these things. Stability and
Okay.
equilibrium, but under vectors, there's also equilibrium forces. So you can look them up.
Okay.
Okay, so that is all here, right?
Yes.
All right. So question B, which this one should be the last one in this paper, is saying a copper wire of length 1.4 meters is fused at one end of a steel wire of length L. The cross section of the copper wire is 2 times 10 to the power minus 4 square meters, and that of the steel wire is 1 times 10 to the power minus 4 square meters. Each piece of the composite wire is subjected to a tensile force of 4.00 times 10 to the power 4 newtons. Question 1. If the extension in both wires is the same, let's take note of that. The extension is the same. Find the original length of the steel wire. Find the original length of the steel wire. Question 2 is saying find the stress in each wire if it is subjected to a tensile force of 6.0 times 10 to the power 4 newtons. Hence, find the strain in each wire. So they've told us to say the extension of these wires is the same. And they've given us to say the copper wire has a mass or a length of uh, 1.2 or 1.4 meters. So let's do this. This is question B. Question B like that, they've given us to say copper wire. So I'll write it as CW has a length of how much? 1.4 meters. And then it is fused to a steel wire. So I'll put S wire here. It is fused to the end of a steel wire which has length M. The cross-sectional area, they've given us cross-sectional area of both wires to say the one for the copper wire is 2 times 10 to the power minus 4 square meters. Whilst the one for the steel wire is 1 times 10 or 1 times 10 to the power minus 4 square meters like that. Then they've told us to say this composite is subjected to a tensile force. So which means the force that is applied to on both of these guys at the same time was of a magnitude 4.0 times 10 to the power 4 newtons like that. And the question 4 is saying, I mean, question 1 is saying, if the extension in both wires are the same, find the original length of the steel wire. Okay, so what are we going to do in order for us to find the length of the steel wire? So we're going to use the formula for extension. Under my properties of matter there, we know to say change in L, or sometimes referred to as extension. So you can refer to it as change in L or E for extension. This is equal to what? It is equal to the force applied multiplied by the initial length over the cross-sectional area multiplied by the Young's modulus of that particular element. Do you remember this formula?
Yes, I do.
Okay, I hope you're not lying, but yes, that is it, the formula. So F is for the tensile force, of which they've given us the tensile force in the question. L is for the original length. We have A for the cross-sectional area. They've given us both cross-sectional areas for the copper wire and the steel wire. Then the Young's modulus here, we have to use the Young's modulus for the copper wire and the steel wire. So one statement now that they said the extension is equal in both wires. Equal both wires like this, which means if I'm using this formula for extension on the copper wire, and I'm also using this same formula for extension on the steel wire, that means the values of their extensions should be the same, right?
Yes.
And if they are the same, don't you think we can equate these two equations?
Yes, we can.
Okay, I can get the doubt in your head. So we're going to say extension of the copper wire is equal to what? Is equal to F multiplied by L over A multiplied by Young's modulus, of which the extension for the steel wire is equal to uh, tensile force multiplied by the initial length over cross-sectional area multiplied by the Young's modulus for steel. So since the extension of copper and the extension for steel is the same, that means you can equate these two equations since they have to give us the same value. So I'll say the tensile force over multiplied by the length, the initial length of the copper wire over cross-sectional area of the copper wire multiplied by Young modulus of the copper wire should be equal to the tensile force multiplied by the initial length of the steel wire over the cross-sectional area of the steel wire multiplied by the Young's modulus of the steel wire. Do you get any sense from this now?
Yes.
Our goal is to find the initial length of the steel wire because that is what we are missing in the question. So the tensile force is the same on both equations, right? I mean, in both sides, since the tensile force has been applied to a composite of these two guys when it was already fused together. That means the tensile force that is being applied on these guys is the same for both wires. So we can simplify our equation further by doing that. Okay, so from here, uh, we're going to remain with the initial length of the copper wire over cross-sectional area of the copper wire multiplied by the Young modulus of the copper wire. This is equal to the initial length of the steel wire over the area of the steel wire multiplied by the Young's modulus of the steel wire, like this. So we've been given to say the initial length for copper is 1.4. The initial length for steel is what we are looking for. The cross-sectional area for copper, we say this 2 times 10 to the power minus 4 square meters. Whilst the cross-sectional area of the steel wire, we said it's 1.0 times 10 to the power minus 4 square meters, like that. Okay, so from here now, what can we do? What are the values of Young modulus for copper and steel? These, they have to be given on the first page of the paper. Now this paper is rubbed. It's a bit, it's blurry. I don't think we can even see what's there. Yeah, I can't see, to be honest. Even here, I don't know. I can't see anything. Okay, so uh, we have to use the Young's modulus now for the copper wire and the steel wire. So both of these are known values. So maybe I can write them here. Young modulus for copper and the Young modulus for steel. Can you give me the values for those two guys? Hello?
Hello? Oh, sorry, my mic was on. Um, the Young's modulus for steel should be 2 times 10 to the power 5 newtons per millimeter squared.
To the power 5.
To the power 5. Hmm.
To the power 5. I reject that one. I strongly rebuke that one.
Sorry. Hmm. I remember it.
Yes, you are
Uh,
wrong on the part of the power.
but everywhere else is okay.
The what? Oh, yeah, the first part. The
Ah,
first
okay.
part, you said it's 2 times what?
2 times 10.
Hmm? Number questions on like page 1, this one like primal values. Yes,
I think I forgot it.
forgotten.
Yes.
Okay, so let me just check. I have a much clear paper.
Okay.
So the Young's modulus for copper is 110. 110 times 10 to the power 9 newtons per meter squared. Whilst the one for steel is 200 times 10 to the power 9. But these are simplified further. That's why this is written as 2.0 times 10 to the power 11, whilst this one is 1.1 times 10 to the power 11 Newton per square meter, like that. Okay, you don't remember anything like this. Maybe they didn't give because they knew to say you understood.
I think they gave us at the end, actually, when we were writing the paper, they brought the Young's modulus at the end.
Oh, they brought car?
Yeah, they told us at the end.
Oh, yeah, because they are supposed to give. You can't dream of these figures. Okay, so we can now
Mhm.
go ahead and plug these into our formulas. So we have 1.4 as the initial length. Then we have the air cross-sectional area. We've said the cross-sectional area is 2 times 10, 2 times 10 to the power minus 4 meters squared. This is meters, and this is multiplied to um, okay, have I swapped the young module? Oh no, it's the same. So multiplied by 110 times 10 to the power 9, and this is equal to L of steel. This we don't know. Multiplied by the cross-sectional area, which is 1.0 times 10 to the power negative 4 there, square meters, multiplied by the Young's modulus, which is 200 times 10 to the power 9. All right. From here now, we can continue with our calculations. So we are going to say, or we can cross multiply. Okay, first find the product of these denominators here. Even there. The product of the denominators. Okay, so I have 2 exponential minus 4 multiplied by 110 exponential 9. Okay, so I'm getting 1.4 over 22, 22 million. Okay, this is equal to that L there over 1 exponential minus 4 multiplied by 200 exponential 9. I'm also getting 20 million on the other side. How is that possible? I mean, oh, this is 20 million. The other one was 22. Okay, like this. So this is what I'm getting. If I cross multiply this, I'm going to get 22 million L for steel. This is equal to that multiplied by 1.4, giving me 28 million. And that divided by 22, like that. So I'm getting L2, or the length of steel, which is equal to 1.27 meters. Have we found the same things?
Yes.
Okay, so that was all on part 1. This is only for part 1. Then part 2 is saying, find the stress in each wire if it is subjected to a tensile force of 6.0 times 10 to the power 4 newtons. So find the stress in each wire. So stress is defined as force per unit area. So the formula for stress, this is part 2. Stress is equal to force per unit area, like that. Okay, and they've given us to say the tensile force is 6.00 times 10 to the power 4. And we know to say the cross-sectional area of the copper and the steel was given. So I'll say for copper, stress is equal to 6.00 times 10 to the power 4 over the cross-sectional area, which is 2.0 times 10 to the power minus 4 square meters like that. And this is supposed to give us how much? The value. Can you kindly help me punch real quick? So it should give
Alright.
us, sorry?
Oh, I was just saying, alright. So let's I've just found 3 for the first one.
Yes, what have you found for the first one?
3.
Just 3.
Yeah, 3 times 10 to the power 8.
No, you are copying my answer. I've already written that.
No.
Okay. This is meter squared also, and this should give us what? For steel, we should get 6.00 times 8 pascals like that. So that is the stress in each of the 2 wires. Okay, if that is the stress, we can go to the last part of the question, which is saying find the strain in each wire. Find the strain in each wire. So what is the formula for calculating strain? Strain is equal to what?
Should be change in length over initial length.
Okay, change in length over initial length. But if we want to calculate change in length, that means we have to start bringing up those formulas again we were using first, you remember?
Yes.
Okay, but sometimes we can also express strain uh, in terms of stress and Young modulus. Do you know that?
Oh, I actually did the first 2 questions only. And I can't remember what I did, so this was a good refresher. I don't think I did this last one.
Okay, so you can also express strain in terms of stress and the Young's modulus. We are from calculating stress for each wire here. And the strain is also what? It is also equal to stress over Young's modulus. Unless you have the time, you can bring back those formulas to calculate the extensions first, saying F multiplied by initial length um, over area multiplied by Young's modulus. You're supposed to do that. But in this case, we can express it in simple terms like this one. So strain will be equal to what? So strain for the copper wire, copper, this will be equal to, we found the stress of how much? We found the stress of 3.0 times 10 to the power 80 pascals. And we're going to divide this by the Young's modulus, which is 110 times 10 to the power 9. And this is going to give us how much? This is going to give us how much?
I found 2.72. So when you round it off, it's 2.73.
Okay, stop copying my answers, eh? This one
No,
will
I'm
be
not
equal
copying
to
the answers, sir.
6.00 times 10 to the power 8 over the Young's modulus, which is 200 multiplied by 10 to the power 9. And this is going to give us how much? It is going to give us, let me punch real quick. 3 times 10 to the power minus 3, like that. So strain, this is just a ratio. It is the ratio of change of length to the original length. So if you put units, that means I don't know who taught you properties of matter, but this strain is supposed to be just like this. Is there any question, please?
No.
Okay. Thank you very
Hmm.
much. This was the last question. The only thing remaining is multiple choice questions. But do you still want us to revise multiple choice questions?
No. I think the multiple choice questions from the past paper that we did last year were part of other past paper questions. I'm not really sure about others, but on my part, I think I'm okay.
Oh, all right. So if that's that, I think today's class will end here. And
Okay, thank
if
you.
you have any of your test papers that you wrote, send them to my inbox so that we can look at them next. Because tomorrow we're also having physics, but if we are done with this paper, that means we have to start something else tomorrow.
Okay, I'll be sure to check through my files. Hopefully, I still have them.
All right. Thank you very much.
Thank you.